Hello everyone, welcome to our first video lecture. This one is targeted mainly for students in section 2, which is my section, so that we can get caught up with the material in section 1. So after this, we will be producing lecture videos that are common to both lecture sections. So today, what we'll do is carry on with the pipeline processor and in particular talk about pipeline registers. What we'll be doing is adding a bunch more D flip-flops in the form of these pipeline registers. Now these are unlike the general purpose registers. These registers have more than 32 bits, sometimes as many as over 100 bits. So, and the updates, of course, are made on the positive clock edges. So let's now have a look at the processor with the pipeline registers now in place. And this is the figure from the textbook, figure 7.46. Okay, so let's bring up the processor. Here it is, with the pipeline registers. And here they are. There's 4 of them. They separate the individual pipeline stages like so. And the other thing to note, of course, is what we've just highlighted there is the register file is written on the negative clock edge. Everything else is positive. And the purpose of the pipeline registers is basically to communicate information from one stage to the next. So, and then carry on with a new instruction. Okay, and so the naming convention for these registers basically are the pipeline stages themselves. FD stands for the pipeline register that separates fetch and decode, and then decode and execute, and then execute and memory, and finally memory and write back. So what we're going to do is much the same thing we did for a single cycle processor. Let's check out an R-type instruction for this pipeline processor. So here we are at the start. So the program counter is read. That is the address of the instruction. The instruction memory reads the instruction word and places it directly into the next pipeline register. So meanwhile, we're able to calculate the address of the next instruction by adding 4 to the PC. And that will become our new PC once the active edge of the clock occurs. On the other side of the pipeline register, we have the instruction word, and from it we need 3 important pieces of information. Basically the 3 registers involved, so 2 source registers and 1 destination register. And the register file reads the contents of the 2 source registers and places those contents into the next pipeline register. And the third thing, of course, is the destination register, which we're going to pass along the pipeline to the very last stage. So in the execute stage, the ALU gets the contents of the GPRs, general purpose registers, and again we pass along the destination registers, the write register, to the next pipeline stage. So, and also the answer from the ALU. So the result of the R-type instruction. Now in the memory stage, we're not really using it. We're simply bypassing it. And so we're going over top of the memory and straight through the next pipeline register. Okay, so just the 2 important pieces of information there. The answer, so the output of the ALU, and it will make its way back to the register file, and it will be input to the WD3, write data 3 input. Okay, and so we also need this other important piece of information. Which register are we going to write that into? So that makes its way back to the A3 input. So this is called write reg W. So there's the A3. So that's the data path. Now we haven't shown the control path. We'll talk a little bit about that later. Okay, so let's now examine the same thing for an R-type instruction in a little more detail. let's talk about individual signals and such. Okay, so let's say, for example, we have an SLT instruction, and let's place it at an address in the text segment at 400030. So it'll be a set on less than instruction, and the three registers we'll be using, 2, 4, and 5. So the first one, 2, is the destination register, and then 4 and 5 are the two source registers. Okay, so let's begin with the fetch stage. So first thing that happens is the program counter gives the address to the memory and to the instruction memory, and the instruction memory provides the 32-bit instruction word to the F/D register. So 32-bit instruction word for the set on less than instruction. And also it calculates PC plus 4, and that is written also to the pipeline register. So it's not going to be used later for the R-type instruction, but it is for compatibility with other instructions. And just a word about the convention that the textbook uses here for naming the register fields here. So basically the first part there is the name of the register field. And the second piece, the capital F there, represents the stage, the pipeline stage, in this case fetch. Okay, now just a word about the clock edge. So remember, these are pipeline registers are all positive edge triggered devices. And so when the next positive edge of the clock comes around, data is written to the F side, from the F side to the D side. Okay, and now the fetch stage is completely done with that. It's washed its hands of the current instructions, and I can go on and get the fetch the next one. So meanwhile, our SLT instruction is now in the decode stage. And so what gets passed on to the next pipeline stage, first of all, what's needed for the R-type instruction. So basically the contents of our two registers. So this was 4 and 5. So RD1, RD2 from the register file. Contents of those two registers. And as we pointed out earlier, what also needs to go along with that is the destination register, which was general purpose register 2. Okay, and again for compatibility, we're still passing a lot of other stuff down the pipeline, not used for the R-type, but this is one of our source registers, and the sign extended 32-bit constant, which of course we're not using, so that would be used for other instructions. And we're also passing along the program counter, PC plus 4D now, D because it's in the decode stage. Okay, so again, just to summarize, this last bit of information here might be needed for some other instructions, but we don't need it for the R-type. So it's there for compatibility. Okay, so moving along, our SLT instruction is in the execute stage. Okay, and so let's keep track of what gets written to the next pipeline register, the E/M. So beginning with the important stuff relevant just to the R-type instructions. So first of all, the answer. So the result of the SLT operation. And also the zero output of the ALU, which again we're not using for this instruction, but it nevertheless gets passed along. And of course instruction bits 15 to 11, which once again gives our destination register. Okay, so two important pieces of information being passed along. Okay, and so again, some stuff that's not needed. PC branch. Well, we're not branching, so we're not using that, but it gets passed along anyway. Okay, so memory stage. And so, as we pointed out earlier, this stage is not being used, but we still have to count it. So, data is passed straight through. So the ALU output. So this is again the result of the SLT operation, and the destination register. Again, this is register number 2. Okay, so the memory stage does not touch either of those, just passes them straight through. Okay, and again, extra information not needed for R-type instructions. And since we're not using the memory, the memory is used anyway, so its result goes into the pipeline register, but we're not using it. Okay, finally the write back stage. So after the clock edge, so now in the write back stage, so the contents of the M side have been copied over to the W side, from the memory side to the write back side. Okay, and so there were just 2 key things here. So again, it was the ALU result from the execute stage, so the result of the SLT operation, and then where to put the answer. Which register are we using? So in fact, it's register number 2. And so the write to the register file occurs now on the next negative edge, clock edge. So remember, we circled the inversion bubble on the clock input to the register file. Okay, and this occurs a half cycle, or right smack in the middle of a main clock cycle. All right, so that was the data path. Now let's take a quick look at pipeline control. So the control path. So there's the control unit involved here is exactly the same as used in the single cycle machine. Okay, so the only difference, of course, is that the control signals must arrive at the correct pipeline stages through the appropriate pipeline registers. Okay, and so this is done in step with the data for each instruction. So the control signals follow the instruction or the data path. So for the set on less than instruction, for example, in the write back stage, so there's two controls there. So mem to reg that controls that last multiplexer, and reg write, which is what the way we need to tell the register file that we're going to write a register into it. Okay, and so these signals are passed through the pipeline pretty much untouched until they're actually used. So, and this is the path that they take. So through the decode execute stage, execute memory, and finally the memory and write back. And so it's in the write back stage that these guys are actually used. Okay, so here's just the control part of it. So for example, you can see the two signals on the top right there, reg write W and mem to reg W. So those are used in the register file in the write back stage. So they're not touched along the way. So control signals are sort of branch off appropriately into the stages that they're used Okay, that was a quick tour of the pipeline processor. And of course, this all assumes that we had no hazards. And so our next topic is then how do we handle hazards? And so that's our next lecture.